Welcome to the lecture number 14 of the deep learning course. In this session, we are going to talk about the various loss function for the neural network. This class is going to be very important, and most probably it is going to tell you very interesting thing about the neural networks. Okay, so let me start my discussion by showing you this a small neural network. So you can see that there is some x1, x2, x0 kind of input that is going inside this, and you have a neural network circuit from here to here. So in between something is happening, and you, as you always think that when you are feeding something to the system, when you are feeding something to the system, you are going to get some output. So input output, this input output thing is not new for you. And how sometimes what happens now, generally our setting is this, that here the number of classes are actually two. We think that two class classification problem, but there could be some setting where there could be multiple classes. Then we say that multi class classification problem. So right now this setting is a multi-class classification problem where I'm telling that let's assume that whatever going to be fed as input can have three categories. So here I'm writing that let's assume that three category could be cat, dog, or lion. Okay, so if something is something being fed to the system, and we assume, let's assume that it is what, it is an image, and we want to tell that whether there is a cat, whether there is a dog, or whether there is a lion. So it is a multi-class classification problem. So there is also one variation of this kind of problem where we say that multi-label. In the multi-level setting, what happens that on the same image, it may be possible that the lion and cat and dog both are there, lion are both are there. So multiple things could be there into the same image. But right now, to make the thing simple, let's assume that we are into the multi-class classification problem where multiple classes are there, but the item that I'm going to provide is going to be into one class only. Okay, in this setting, let's assume that at a particular time I'm going to feed some input. Okay, let's assume some input I am going to means I am going to feed, and then I want to measure that what is the output that is going to come across these neurons, output neurons. Let's assume that the output coming across the first one is S1 and S2 and S3. These are the three output values that I'm going to get. So you may think that S1 could be 0. For example, 0.82, S2 could be 0.52, S3 could be 0.33, something like that. So if this is what the output that we are going to get, so can anybody tell that what is this particular item, whether it is cat, dog, or lion?
Cat.
What is this?
Cat.
Is it going to be the cat? Because you can see that it has a highest value, so it has the high thing. So therefore, you are going to tell the it is going to be the cat. Sometimes what happens that you want to represent these things, whatever the output that is going to come to you, you want to represent this as a probability. Okay, so that you can directly interpret it as a probability. So how can I do that? So you know that there is a very important property for the very important thing for the probability, that the summation should be what? Summation should be 1. So there is an idea that is called the softmax, and that tells that after this you are going to apply something called softmax kind of layer, and that actually tells that whatever output you are going to get, you are going to put this value over here, and underlying there is a summation of all the values which are there for all the possible summations. So what is here? What is the I for all the classes that we have? We can write for all the I inside the classes. You are going to find out the summation, and you can do like this. The basic idea is this, that the output that was 0.82, you are going to tell it now e to the power 0.82 divided by 0 e to the power 0.82 plus e to the power 0.52 plus e to the power 0.33. In the same way, the next value such as 0.53 can be converted as e to the power minus 53 divided by the summation term that was here. And similarly, 0.33 can also be converted by saying that e to the power minus 0.33, e to the power e to the power um, it is not minus. Okay, 0.33 divided by the summation term, the same summation term. If I change this, what is I'm going to obtain? So one thing that I'm saying, because here is an exponential function, so property of exponential function is this, that if something is larger, even if the small by small portion, it actually try to amplifies that. If something is larger, it becomes more larger as seen, because now it is an exponential function now we have. So this function actually, that is called the softmax function, actually does this kind of very important thing, that you apply in the output as a softmax function. Any problem on that? The first thing that I want to tell to you, that whatever output you are going to get in your neural network circuit, you are going to apply a softmax on that, and then this is going to represent what is the probability of the things. So output, we expect this value. Now we think that if S1 is going to come out, I'm going to represent it. I'm going to apply a function that is a softmax function, and this is going to be this particular value. Any problem in this? Very standard kind of thing that we have not discussed till now. That's why I'm telling this to you here. Make sense? Any questions on that? Okay. Let me come back for a minute, and let me give you something else, one more thing to you. And this actually means that, because you know that whenever I'm going to provide something to the circuit, I may not be getting the exact output, because initially when I started, my values are not set. So I have to train the system, and after training, my things would be right. For example, if I'm going to feed a image of a cat, for example, when I am going to feed a image of a cat, this value should be 1 and all other values should be 0. What I need the output as 1 0 0. If I feed the image of a dog, I need this output 0 1 0. I want this kind of output. Okay, so if I want this kind of output, and my output is something else, because I don't know that, because of the parameter initially that are not set. If I want to find out that how good I am, again you have to define a loss function. Okay, you have to define a loss function. How this loss function can be defined? So you know that these are the values that actually I want: y1, y2, y3. These are the, for the, what is the first value, what is the second value, what is the third value that I'm expecting. And let's assume that the image is of the dog, for just the sake of clarity. So this is what my output that actually I want. But what my value is, it is going to be provided by my network circuit. I'm not sure about this. Okay, so let me call it that by doing some computation, the value are going to be right now, what I'm telling. I'm telling that they are S1, S2, and S3. What I'm telling, that they are S1, S2, S3. So the actually, if you want to find out that how much loss I have, how it is going to be, how you are differing with the actual values that you want. So you can say that it is S1 minus Y1 plus S2 minus Y2, and as usually you apply a square function on that you want to S3 minus Y3. This is what it value. Any problem on that? You can very simply say that this is going to be this particular quantity, summation of all these things. Since I'm going to train this on the multiple values, I can say that for every training sample, I'm going to find out this particular quantity, that how much they are going to differ. So if my system is going to be correct, if let's assume when my system is completely trained, this value everywhere, the same value I am going to get, what I expect, that I only expect this thing. Everywhere my same value that I wanted from the network, out as an output, my network is giving the same thing. The value that I wanted as an output, my network is going to give me the same value. So all these values become 0. So ultimately loss would become 0 when my network is completely trained, but initially the network would not be trained. So this is what the general methodology that we actually follow to define the loss, and then we actually train our system. Then we train our system to reduce this particular loss. Any problem on that? Hope this is also clear. Everybody, are you clear that in this way we can find out that what is the loss of my system, and our objective would be to reduce this particular loss? Yes or no? Yes or no? Yes. Okay. Look what happens. The problem is this, that this particular in the classification kind of setting, when my output is going to be there, So as I told you that whatever the network output was coming, I'm not going to use this output. Instead, I'm going to apply some kind of e to the power something. And we a few minutes back talked about that I'm going to convert that loss into some different value. So what do I mean by this? That the value that I'm going to get put it over here is going to be different than the actual value that I was actually actual value that was actually coming from by the computation of all these things. This brings a very different kind of problem to our system. Look, how can we reduce this loss? What was my basic philosophy? My basic philosophy of reducing the loss was the gradient descent. Okay, gradient descent. We actually, with respect to the every weight, we actually find out that what is the derivative of this particular quantity, and we go into the direction where this particular loss is going to be reduced. We have seen earlier that any gradient descent kind of method is only going to succeed if this function is going to be convex. Then only this thing is going to converge. But now, after applying these kind of thing, what happens that this function ceases to be convex function. Now this function is not convex function. Okay, then it becomes a very big problem that we have formulated a problem, but now we cannot do the optimization because this is not a convex function. Why this is not a convex function is again a very is something that need a lot of mathematics to explain. So if you are interested, you can go to see one of my lecture, that is ktheory.in, on ktheory.in on my own website. If you go there, there is a machine learning course that I offered last semester. Here there is a, if you go into the resources, you can find out this lecture number 20 and 21, linear regression and logistic regression. Can you see this lecture number 20 and 21? In this lecture, if you are interested, you can see this to find out more that why this particular function is actually not convex function. I'm not going to into the much detail that why it is not convex function, but it is not convex function. Right now, you think that you assume that this function is not convex function. So we cannot utilize this for reducing our error. So therefore, a different mechanism need to be developed. So in this lecture, in that lecture also, we have talked about that there is another method that is called the cross entropy. So into the cases where we are actually going to do classification kind of thing, cross entropy is a better function to represent the loss. What is the cross entropy? Cross entropy function is defined in this particular way. For example, for all the classes that we have, we can write it yi log of whatever value that I'm going to get out of this. So this particular function is called the cross entropy function. So we should use minus of this particular quantity. Why minus? Because you know that this particular function f was defined using this criteria, and it is going to be less than what? Less than 1, and therefore the value is going to be definitely going to be negative. So if I put another negative over here, it becomes positive. Nothing more than that. So this is a function that we are going to use once again. So what I told you, that the general method that actually you use, that you see that what is the difference of this particular quantity with the expected value, is not going to work, because into the classification kind of setting, this function ceases to be a convex function. So instead, it is better to use another function that is a class entropy based function. So this is the function that we can utilize to find out how good, how bad my function is this, and then we want to reduce my badness. Any questions on that? So there are two summation term. This particular term is again the only this terms actually is with respect to a particular input. For all the classes, you see that what is this particular value, and then you actually take the average on all the possible values which are over there, because all the training examples, you find out the average, nothing more than that. Let us closely look this particular function to just give you some better idea that why this, what is the, Akshit is asking that why there is a log. Okay, so why there is a log? As I'm telling that I'm going to use log only just to represent something. You know that if some value is actually, if there are what I wanted to tell, let's assume that I have a value x. I want to maximize this value. Okay, so if I maximize, instead of maximizing x, so let's assume that on some value, or should I say in this particular way, that if there is a function that takes some value x, and I want to find out what is the maximum value, means on what value of x this particular function gives me the maximum thing. Okay, let's assume that I wanted to find out that. So instead of this, if I write 2x, is there any problem? Same value. Okay, on the same kind of settings, it is going to give me the maximum value. Okay, so same kind of setting we can utilize that if we want to maximize this thing for a particular parameter, so that parameter would also maximize the log of that particular thing, because log of that thing would also be maximized on that particular parameter. So on the parameter where x is maximized, on the same parameter 2x also is maximized, on the same parameter log x is also going to maximize. But by applying the log, we are actually transforming the data in such a way so that that it becomes a convex function. Once again, if you want to see more, I request you to see that lecture number 21 and 22 are the machine learning course, ML course. Make sense? I'm not going to much detail because otherwise I would deviate from things that I wanted to teach you. So right now, what I wanted to say you that using this kind of function that is called the cross entropy function, this function is going to uh, be a better function. Let us see this function more clearly, more closely. So you know that I am going to define the loss into this particular way for the and this particular term is only to find out the average across the thing. So let us just focus on one particular item. Also, let us also think that this number of classes is 2, just for the sake of simplicity. What would happen that this function you can consider in this particular way. You can say that for I is equal to 1 to 2, you can say that for I is equal to 1 to 2, this particular quantity. Any problem in this? Same thing I have written. What I wanted to tell you over here is this, that I can open this, I can say that because y is there, so y1 multiplied by log of fs1 plus y2 log of fs2. Can I write like this? Yes or no? Can you write yes or no? Akshit, yes, okay. But please note, if we have only two classes, for example, class is y1 and y2, two classes there, and if the value of y means what? Value of y is what? So 0, let two classes be 0 and 1. If this is 1, then probably this is 0. If this is 0, then this is 1. Only two classes are there. So I can say that y2 is equal to 1 minus y1. Okay. Can I write like this? Because only two classes are there. So if I say that what is the value of y1, then y2 value can immediately can be found by saying that 1 minus y1, because they are counterpart of each other. So we can write the equation like this. In the same way, if I find out that what is my output given by here, so since you know the summation is going to be for all the classes is going to be 1, so you know that f of s1 plus f of s2 is equal to 1. So if I want to find out f of s2 is equal to 1 minus f of s1, so I can put again here s2 can be written into this particular way. So if you think that the formula that I have written is actually different, that the thing that actually look into general settings, so you can see that this is the same formula that most of the time we actually talk about into the logistic regression. This is the same logistic regression formula. Make sense? All right. So what I was telling, that using the class entropy, we can define the loss into this particular way. And let me more simplify this by writing this equation, by this loss function, by writing this thing. So what is this? What is this? I'm telling. So what is going to happen actually what happens now is, let's assume that there are only two classes or multiple classes. Let's assume that the output is going to be 0 1 0 0 1 or 0 0 0, because only one class. We are thinking that multiple classes are possible, but the item would be into one class. So this kind of output we are going to expect. So if we put these c time summations, what is going to happen? So multiple terms would be there. So with the 0 multiplied by y1 multiplied by log of f y1 log of f s1 plus y2 multiplied by log of f s2. Okay, am I right? I'm writing in, my writing is not that good, so I can write that y I log of f s2 fsi, like that. So this is going to be the term. So what happens, since I'm expecting that there would be only one class, so there would be one place there is 1 and all other places there would be 0. So what happened, even if I'm going to find out the summation, it is going to be do what, that all the terms are actually get cancelled, only one term is going to survive, and that term, let me call it that this is the target class. What is the target class? positive class. Which is the positive class? If I say that there is some class which is actually positive, I can say that what is the output with respect to that particular class. If I find out the output with respect to that particular class, once again, multiple outputs were there. Once again, into the output, multiple outputs are there. I am telling that one of them is I am only going to see that as a 1. And if I find out that what is the output with respect to that thing, so I can immediately write that e to the power sp, because output was e to the power that thing and the summation of all other things. So this summation term also I can remove. This summation term I can remove if I write here that what is the value with respect to the positive thing, because this is the only thing that is going to contribute. Make sense? So the simplified last function can be defined into this particular way. Any problem in this? How will the equation simplifies if there are 3 classes? Okay, so as I told you that I think we have not discussed this into this particular class. So 3 classes can be can be can be thought as 1 versus all. In all the cases, you can think in that particular way. That in 1 versus all you can always define, and then if you try thinking into that particular way, so you can create a kind of tree-like structure where only one thing would be there and all the things would be actually taken as a rest class. Make sense? So there are other methods also, but right now just think that into the setting when multiple things are there. If we want to analyze, all other things can be placed into that. They are not like that. So this particular equation is in that sense going to be very general, and whatever thing you are going to consider, you consider over here, and a proper probability of all other things are going to be summed over into this particular output. Okay. Okay, all right. So this particular thing, what I was telling, that last function is now defined using this particular formula. Very simplified formula, very elegant formula that we can define into this particular way. My question is that if I have very simple question. If I can train my system using this kind of thing, how, whether the and the last becomes 0, whether my system would be correct? Yes or no? Whether my system would be correct? Definitely yes. Because if this is going to be 0, then all the things are going to be rightly classified. Okay. So this is the one method, very basic method to find out the to train the system, to find out the right weight. If you define the loss into this particular way, you can train your system in an effective manner. Any questions on that? Clear? Everybody, can everybody write yes? Akshit, yes. Okay. Now let me tell you a very simple thing, that in the last class we have discussed that when we are going to provide something as an input and we want the class labels to be output, so it is not like that. It is going to be a very simple thing, because if you provide some input, so if you provide some input, okay, so it is going to do multiple things. For example, enhancement, you want to do some enhancement, then you want to apply some attention, then you want to find out right kind of feature, then you do something, and at the end you apply a kind of classification head, and then you find out that what is your classification. Generally, if you don't apply the deep learning, you have to follow this particular pipeline. You understand? So even if you are going to apply the deep learning, it is, as I told you in the last class, that it is again all these things. You can think that okay, however it looks like the big network, but in essence it is going to have multiple parts. After that it is going to do something. Do you agree with me or not? All those components would be here. Okay, you are, some network part would be doing some things with related to all these things, and that's why they are going to produce you some kind of right output. Make sense? So if you understand this particular part, let me decouple two important component. One component is this, that after getting the feature, how I apply the classification head, and here I can say that I apply the weights over here, and I find out that that what is the classification. So I can say that there is a classification head, and in between, before than that, everything is going to compute whatever is going to compute something. At the end, it is going to give me a feature. Can I say like this? Can I say like this? You understand that there are multiple parts, but what I'm telling that your network circuit is doing many of the things, and after that it is going to come up to the feature, and after that on that feature I'm going to apply a classification head, and I'm going to get the classification out of that using that classification head. Make sense? Here in this particular setting, if I say that what is the feature is this. This is the feature. Once again, this feature is being obtained before the classification head. Anything which was coming to the classification head, before then the feature was actually available. So let me consider this particular thing as a feature. So your input was I image, but actually you out of that you got xi. Okay, that a feature that you are going to get, and after that you are going to apply multiple weight. So whether this is a class, I can say that w1 weight w2 is a vector that actually contains all the values with respect to here. So I can say that there are multiple weights available. Any problem in that? Okay, so I have defined the loss into this particular way. I have defined earlier the loss into this particular way. So what is the value actually going to come if the class is, for example, p class? So how can I define this particular value? What is the SP? SP is the output of something. So I can say that xi that has been computed over here, xi that is that actually got, need to be multiplied with the WP weight that is with respect to that, and then I have to add the bias on that, and this is what the SP is, because this is what the output comes. What is the output? This is what the output is. Okay, so I can change this formula by having this kind of setting where I am going to tell that I am going to consider that there is some I'm going to consider that there is some feature vector inside. With respect to every input there is some feature vector. If I say that, I can visualize this formula into this particular way. Again, I have put this particular extra term. It was not here, but I have put it just to say that ultimately we are actually interested into the average value of this particular quantity that we want to minimize to be 0. So it is fine. Is it fine? This is called the softmax loss. This is called the softmax loss. This is a very good kind of loss. It is separable because if you can train your system using this kind of loss, so it is going to be separable. Separable means it can separate the different classes. So you know that what I mean by this. You know that I was telling this thing multiple number of time. Let's assume that these are the positive class, these are the negative class. I want to find out the feature. So if I want to find out the feature into the feature space, maybe these points could be somewhere here. I'm not sure about that. These features could be here. I'm not sure about this. It depends upon the kind of transformation that you are going to apply on the data. And I think the better diagram would be, instead of this, better diagram would be this, that if I say that, let's assume, I can say this thing to you. Let's assume that these are the positive examples. These are the negative examples. Okay, so into the feature space, what I can do, I can apply, I can, instead of xy, I can also put one more thing, that xyz, and into the feature space, and the z could be, and the value of z could be computed by I can say that x1 minus cx plus y minus cy square, and this is the value of z that I'm going to consider. If I apply this kind of transformation and create the three-dimensional thing to the system, what would happen? These points are going to get up, and this point, if I say the cxcy to be a point at this particular location, so these points are going to be at the bottom, and all other points are going to be on the space. So we have seen this earlier also, that there is this kind of transformation where we call it a kernel function can be applied, and then we can draw, simply we can draw a line, we can tell that on this hyperplane things are which are actually below, they are like this. So what I wanted to point out at this particular moment, that the representation of the data into the feature space is different. Number one thing, the feature space may be different. You can find out the different representation of the same thing into the feature space. So into the feature space, things become separable. Here also I'm going to see that here I cannot draw a line anywhere, so that the things are separable. But in this kind of transformation, what I got, that now the things are actually separable. So here the things becomes softmax. In here I can see that the things are actually separable. However, we have actually find out that this kind of method is not discriminative enough. It is not very much discriminative. So what do I mean by this? It is separable means you can, if you use this kind of feature, you can find out the right kind of plane that can separate your things over there. But what happens that when you are providing the uh, when you are providing your data for the training, so you on the training data, if the things becomes very good on, but means if the training data actually fills up all the space, for the one class is here and the class is here, if he feels like that, so if a new point is coming, so if the new point is coming, if it is falling here or here, it is fine to find out the classification. But it can go inside here also, and where your boundaries are actually blurred, they are not very much defined. Okay, so what happens actually, what happens that these things are going to be very uh, features are going to be distributed across all the places. So problem is this, once again, the problem with this kind of approach is that I am not going to regularize anything on this particular X. This X could be anything. And this is the hidden representation of the input that I was going to get. And since it could be anything, so generally what is going to happen, it could be something like that, that the two classes are separated, but these features are going to fill the complete space. So that's why they are separable, because now we can draw a line to separate them, but they are not discriminative because they are very near to each other. Just try to see across the boundary. If few items are here, few next items are here, if I ask you that what is the classification of this particular item, you would be confused because it is very near to this and this also. Okay, so this is the problem, that is not that much discriminative. So there is an idea. The idea says, I am going to increase something very interesting for you. So the idea says center loss. What do I mean by center loss? Center loss is something this. For example, if one class items are here, second class, here I'm talking about into the hidden representation. The class next class representation is this. Okay, the features into the hidden representation space are this. So is it separable? Yes, everything is separable. One class items is at one place. This is the class number 1, class number 2, class number 3, class number 4. Can you give me that where is their center? So here it is a center, here is a center, here is a center, here is a center. Okay, how can I find out the center? Just finding out the center, you find out, you know that for all the data item which are actually into this particular cluster, first you find out who are the items inside this cluster, and then find out what is the summation of x divided by number of items, summation of y divided by number of items, and this is how you find out that what is the center. If you find out the center, then you can say that you can define the loss into this particular way, the loss function that actually you were having earlier, plus one more loss that is called the centered loss. It is this, it is the value I'm going to add, that what is the difference between of this particular quantity, that if there is a data point here, so what is this particular distance, this is xi minus, this is the difference between these two vectors, and I'm saying that this distance should also be small. If I find out that what is this particular quantity, it is LC. I say that there is one more component LC. So earlier the loss was L. I am telling that loss plus LC should be small. If I say that loss plus LC should be small, instead of loss, if I say that loss plus LC should be small, what would happen? If I say that loss plus LC should be small, so if I say that loss should be small, so this is what I was getting, that item where separated into the hidden space, their representation was separated by this. But if I say that LC should also, if I add the LC over here, I have to minimize this quantity also. What does it mean? That now these points are going to be shifted inside, somehow they would be shifted to the center, so that the value becomes lesser. So what happens, that ultimately what you will see, that this kind of, instead of this bigger thing, now you are going to get a smaller thing. Your feature are going to be more localized, your feature are going to be more localized, your feature are going to be better. Features of the same person are going to be more similar, that we want now, because if your images should be very near to your images, it should not be that your 10 different images should be different in it themselves. So now the images of the same person are going to be very near. This is a very interesting idea, that is called the centered loss, and this bring this kind of interesting property. Make sense? However, there is a big problem, that determining the center is expensive, because on the complete data now you have to run and find out that where is the center. And there is a and there is a question: will it be always separable with softmax? The answer is that yes, because answer is yes, that we expect that uh, what we are expecting here, that we would be able to train and we would be able to reduce the loss to zero. This is what I'm expecting right now. Okay, if you can do that, so definitely, since if the loss is going to be zero, then you would be getting this kind of separable hyperplanes. Make sense? So here I'm not talking about the different kind of specialized problem where you cannot find out the counter examples where you cannot find out the solution. Okay, in the general problems, I'm thinking that let's assume right now, for the just sake of the discussion, let's think that we are able to train. But if we are able to train, what is going to happen? It is okay. If we are going to train, what is going to happen? That the features are going to be distributed like this. Okay, this is not good, because why it is not good? I pointed out that what happens that for the same person, if the same person, if you see that this is one feature vector, this is another feature vector, they are distance. And if you want to see, you can see that this person feature vector is this person feature vector. I'm telling that they are same. Here is also if you just try to see that closeness of this point and this point and this point, you can by yourself see that looks like that these points are more near as compared to these other points. So the same person images are actually different. The feature representation is different. So this is not good. Do you able to can you able to see that particular point that I wanted to make? That if it is so much distributed of the same person's images, we are more very much distributed into the feature space. What is the problem? That look, this there is this much difference between the same person's image. I have trained the same things, it is fine, but what has happened that in the same persons this much difference is there. But you can see that here is they are more near. This is not a good property. Good property would be there that if they are localized, I want them to be localized. If the features are like this, then maximum distance is going to be reduced. So I want these things should be shrink. This should shrink. For that we have applied this kind of method called the center loss. Are you able to understand this, Akshat? Are you able to understand this part, that why we want this kind of the feature to be centered? So we want the feature to be centered. Okay, but the issue is that finding out center is expensive, because one on the all complete database, then you have to apply your algorithm to see that who are the items which are inside one center. Then you find out that what is their center, and with respect to the center you find out the distance, and then you find out compute the loss. It becomes very difficult to compute the loss. And especially in the cases when actually we are going to train the things into the batches, what happens into batch training, you know that I'm going to train on this, then I'm going to train on this particular data, I'm going to train on this particular data. Then in this case centers are not accurate, because the the center you obtain by this particular part and this particular part are going to be different. Again a big problem. The third problem is more severe, that tells about that most of the time when I'm going to find out that what is the distance between the thing using this formula, it is going to be the Euclidean distance. Euclidean distance is not a good idea, because sometimes we have seen that even to the classification thing, we use, for example, cosine similarity and other similarity measures also. But here I'm going to only put this cosine similarity Euclidean distance. That may not be the right choice for other cases. So these are the issues, that this particular loss function is not good. All right. So let us see this loss function once again. Go visit and try to improve this in some way. So there is a you know that the output you compute by this particular formula, that there is a weight transpose xi plus bi. In this way you compute this. Here always I can say that there is one is also included by this. I can include the bias into the weight itself. I can say that the formula is w transpose x. Every time we can say that. Okay, if you want to find out the output, it is going to be w transpose x. Okay, w transpose x, what is the w transpose x? You know that it is going to be w transpose x is going to be w norm plus norm of xi into cos of theta I. Okay, x1 cos theta, you know that the dot product is computed into this particular way. This is the general definition of the dot product. So if this is the general definition of the dot product, so can I do one thing? That is a very important thing, that this was a network that was going to give you the xi, then after that there was a classification head, and there were the vector. If what if I say that I am going to normalize this particular weight? every time when I'm going to find out that what is the classification, I'm going to normalize these particular weights. So I'm going to tell you very radical thing this time. I am telling that I am going to tell that whenever I'm going to find out that what is the output, I am going to normalize this particular weight. W is normalized so that the value is going to be 1. If I do like this, so at this particular place I was putting this output, and W is 1. If W is 1, so everywhere the e to the power 1 term is going to come as a multiplication. I can take it out. Here also in every term there would be e to the power 1 is coming, so that term get cancelled. So ultimately only what is the value of x into cos theta, I can put it into the expression. I can change this expression into this particular way. I have done what I have done. I have done a normalization. This normalization has a kind of special effect. So what is that effect? So earlier what was happening, that because I have changed this thing into the cosine formulation, what happens, earlier the feature were actually distributed like this. They were filled everywhere. But because the cos formulation is there, so what happens now, the features cannot be anything. For example, here and here and here, they cannot be like that. Now they are angularly distributed. If I put angle into the computation, what happens, they are now angularly distributed. What I wanted to tell, earlier the features were like this. Okay, features were, now they cannot be like this. Okay, they cannot be like this. They can be on the center. They couldn't be distributed into this particular way. Feature could only be distributed into this particular way. They are going to be distributed into a particular angle. For a particular item, that for a particular class, features are going to be distributed into this particular way. Okay, earlier features could be distributed in any particular way, but now because of this cosine formulation, my features are going to be distributed into this particular way. Okay, for one class, items are here. For another class, items are here. For some other class, the items are here. Here. For another class, the items are here. For some other class, the item could be here, like that. They are distributed into the angular way only. Okay. There is one more. There is another one more improvement into the system. Actually, what happens here, we have seen one thing, that what we have seen, that the features are actually distributed here like that. They are angularly distributed. They are distributed into the angular way. Okay, they are now the feature would be distributed into this particular way. One more modification that is done by this Fairface paper, that actually all these papers are very recent. I think this paper came in 2016, 2018, like that. So this particular paper actually talks about this, that instead, because I was telling here I want what, I'm putting cos theta. Instead of cos theta, it is going to tell that I'm going to put a function over here. For the thing which are actually right, I'm going to put a function. On this angle, earlier I was telling cos theta, cos of this particular theta. Here also I was telling the cos theta. So into the function there is a cos theta. But for the right class, I'm going to tell that I'm going to put a function. And this function is very simple. It is going to be telling that -1 to the power k cos of m theta multiplied by yi. It is again the cos thing is only, but he is telling that there is some small quantity k between 0 and m. You pick some small quantity m that is greater than 1, and in between 0 and 1 you put some value k, and using that k you are going to define the angle into various segments, and with every correct item the theta is going to fall into this particular range. What does it mean? It means that because here what was the thing, that everything was inside the circle, I am going to divide the circle into parts. Okay, and alternate thing, I am going to push this. So because if it is a positive thing, I am going to put here push into one direction. It is a negative, because 1 2 3 4 classes are there, the class id is positive, then I am going to push one side. Class id is odd, then I'm going to push into the another direction. So what would happen that the feature which were actually earlier distributed across the thing, now one thing is pushed into this side, another thing is going to side by side, things are pushed in some way. Because of this kind of arrangement, side by side things are going to be pushed into some way, and this creates a decision margin. This creates a decision margin. So features which are, for example, here, feature that were here, now they are going to be here, and in between there would be some space. This we want, because for the same kind of item, features should not be distributed, they should be very near to make the thing better. This paper is called as fair face. Very interesting idea that tells that I am going to apply, for the right kind of thing, I am going to apply a function that is a kernel function that pushes the thing into positive and negative direction, and therefore I can create a decision margin. In this particular formulation, once again, if you just see this particular formulation, and I ask you that, okay, this thing is done, what improvement you can again do? Is there any possibility of improvement? Can you suggest me any improvement? So you can by yourself think that, sir, few minutes back you told that weight was also multiplied over here, you made it 1. Why not you also do some kind of things with the x also? Can we make the x also 1? Can we apply some kind of extra mechanism so that x is also 1? After whatever is coming out, after that I am going to apply a kind of normalization. Because this is not very radical thing, because you know that whenever I am going to feed something to the neural network circuit, we have seen that this particular item is actually normalized. So if feature is going to come, why not you also normalize to the feature? This particular thing is called the hypersphere. And here what is going to happen, that I'm going to tell that I'm going to normalize this thing to a value s. Okay, I'm going to normalize this particular quantity to a value s. If I normalize this, the formula becomes, again, the formula simplifies to the CAS formula. And what is the important thing by this you are going to attain is this, that the multiplication of the weight and x is going to be s, or the fixed quantity. Okay, so what does it mean? It means that the distance of weight and vector is going to be this much, and it is going to be the same. Do you see? Because w is also 1 and the x is also is s, so multiplication become constant. So any item where this particular item, ultimately this is the item, the location, if you want to find out with the cos theta, so all the features are actually going to be distributed in this particular region only. Earlier what was happening, everywhere the feature were there, then we have changed in such a way so that the features are only into this particular direction. But now after normalizing this thing, what is going to happen, they are not, now they cannot be here. All these features are going to be here only. Very, very interesting idea. Once again, see this thing, that earlier your feature was like this, your features were like this, so their distance could be different also. Okay, when we have normalized them, what has happened, that now this is going to come, that they are on the surface only. It may be possible that they have some in between there, they have some kind of, somewhere there would be less space, somewhere there would be high space, so it is possible they have the margin. But once again, it is a better representation. Okay, and also what is the distance between this and this is this much. What is the distance between this and this is this much. What is the distance with this and this is this much. So if I ask that whether this item is similar to this item or this item, so you can say that, sir, looks like that this item is similar to this item. Again, we want to do the same thing, where these items are actually, these features should be localized at this particular point only. How can we modify the formula to do that? Okay, next point, cost phase. Very important paper that actually talks about this thing, and this is the 2018 paper that actually talks about this thing, that here into the formula of cos, you say that because angle you want to modify, you say that there is a separate margin minus m, this should be there. We want a margin of m to be into the formula. Okay, here we assume that my weights are already normalized, and features are also normalized, then you get this kind of formulation. Once again, this is a very interesting diagram that tells that when you are using softmax, your classes were separated like this. When you use a sphere face, your classes were like this, that they were angularly distributed, but they were actually having the things. Now they are angularly distributed. Here everywhere the item were there. Now they are angularly distributed. With the cos phase, what happens? Because the angle pushing, what happens, that you are going to get the things into this. Arc phase says that I want this much, at least this much distance everywhere, that is m, so they are well separated over here. Very interesting result that is actually reported in this particular paper. It is on the face database. So this particular paper that actually we are talking about, that came into this arc face paper, came into 2019 paper. This paper talks about the face recognition results on two databases. This is the labeled faces into the wild, and this is the YouTube face database. These are the very common big databases that the people use. LFW is much challenging as compared to these databases. So for many, why I'm telling that this is much challenging, because for many years people were actually trying to solve the answer, get the answer on the LFW database. So on this database, this arc phase paper was able to achieve 99.83% of accuracy, and YTF database, it was able to achieve 98.02% of the accuracy. One of the wonderful papers that actually is. And earlier, let me tell you that why it is very important, because LFW people were solving the problem. I have seen the people, many of the people papers actually coming out accuracy of around 90%, and for example 85%, then 90%, then 92%. For very long it was stuck like this. After using only the deep learning based techniques, it was possible to increase the speed, increase the accuracy up to 99 beyond 99%. Okay, very interesting idea. So that is the some kind that's all for some of the thing that I wanted to tell today, that in many ways, if you modify the last functions, actually your feature vector is going to be regularized in a particular way, and you would be getting the better representation of the feature, and therefore your system is going to perform better. That's all for today. Thank you very much. If you